In the last video, we saw that when light is incident upon a boundary between media, the manner in which it refracts or bends as it goes into the new medium is going to be a function of the relative speeds of the light in the media. So I have a situation here where light is moving from a slow medium into a fast medium. How do I know that? Well, if I look at how the light bends as it moves into the new medium, here is my theta refracted. If you trace the path of the light that it would have traveled, right, just right up this line. If there were no boundary, the light would continue on in a straight line. If you trace that path, you can see that this ray has been bent away from the normal. What that means, that only occurs when the incident medium is slow and the transmission medium is fast. Now, of course, those are relative terms. This doesn't have to be air or vacuum where light moves as fast as it ever will. It just has to be a medium where the speed of light is faster than in the incident medium. But given that situation, if I have light, and that's a big if I have light moving from a slow medium to a fast medium, I bend away from the normal. Okay, so interestingly enough, just because of the geometry, that I can't bend away from the normal forever. So notice the orange ray that I've given you is some standard refraction, some bending away from the normal. But if I increase my angle of incidence, then I increase my angle of transmission, but faster. A small increase in the angle of incidence results in a larger increase in the angle of refraction. That's easily shown by, let me remind you of the law of refraction. N1 sine theta 1 is equal to N2 sine theta 2. Because N1 and N2 are different, sine theta 1 and sine theta 2 can't be the same. So a small increase in the incident angle represents a larger increase in the refracted angle. So what that means is there's a point where I come in at some angle, which I've called theta critical, the critical angle, at which my transmitted light is actually traveling parallel to the surface of this medium, right? So if I come in straight, I get a ray that's straight, but as I start to bend over, I get a larger bending here. At some point, I reach this angle at which I come in, and the light is traveling straight across the surface of the medium. Well, the problem there is if I then increase this angle a little bit farther, where is this light going to bend? It can't bend anymore and stay in this medium. And what actually happens is it doesn't transmit to this medium. If I come in at an angle larger than this critical angle, I get the light not transmitting, but actually just reflecting back. Now we know at any boundary, I expect part of the light to reflect, but at these angles higher than what I've called the critical angle here, I get 100% reflection. I get nothing transmitted. In other words, I can't transmit it because this light can't bend anymore, and so it just stays in this medium. This is called total, let me write this down, total internal reflection. Notice it only happens if I'm moving from a slow to a fast medium. If I'm moving the other way, I bend towards the normal and I never reach this point where the light is traveling parallel to the surface. But if I'm moving from a slow medium to a fast medium, I reach this angle, the critical angle, after which I experience total internal reflection. Any light incident upon this boundary will not be transmitted to region 2. It will just be reflected back into the first medium. Okay, so how do I find this critical angle? Well, the answer comes from geometry. So notice at this critical angle, the angle of refraction, which is always measured from the normal, is 90 degrees. Right? If it's traveling parallel to the surface, and I've drawn a normal line. What those words mean is that this angle, this refracted angle, is 90 degrees. So how do I characterize that, or how do I find the critical angle? Well, I let my angle of transmission be 90 degrees. Let's call that theta 2 just to match up with what I've drawn here. Again, it works both ways as long as you're consistent. Doesn't really matter what you call 1 and 2, but I've already labeled them here, so let's be consistent. So sine theta 1 then is going to be my theta critical. So I'm going to get N1 sine theta critical is equal to N2 sine of theta 2, but we just said that that's 90 degrees. And the sine of 90 degrees is just 1. So N1 sine theta critical equals N2, the index of refraction in my second medium. So it looks to me like sine theta critical is equal to N2 over N1, which means theta critical is equal to the arc sine or the inverse sine of N2 over N1. And there you have it. Notice there are some restrictions to this, right? If theta critical equals the inverse sine of this ratio has to be in the range of sine, which ranges from -1 to 1. In this case, we're just going to let it range from 0 to 1. All we care about is the magnitude, which means that N1 has to be bigger than N2 for this fraction to be less than or equal to 1. Well, to be less than 1, N1 has to be bigger than N2. But isn't that what we already said? N1 has to be bigger than N2. Remember, the larger the index of refraction, the slower the speed of light in that medium. So I will never get a critical angle coming the other way. We've talked about it physically. It bends towards the normal. Mathematically, is because that would that would give me a numerator which is bigger than my denominator, which according to this doesn't exist.